So we'll continue the analysis of power system stability using classical methods. So yesterday we have started, in fact, the transient stability analysis, right? We discussed about the small signal stability of a single Mason infinite bus system, and also we started the transient stability analysis. And in the transient stability analysis, we are about to start the equal area criterion, and we are discussing how the equal area criterion is very advantageous to quickly assess the transient stability of a system. So let us consider this system where this is a single Mason infinite bus system, and here the PM is your mechanical power input to the synchronous generator, and this is constant as per our assumption. And E delta is your internal EMF, and delta is the rotor angle. And V infinite 0 is your infinite bus voltage. And this single Mason is connected to the infinite bus through a transmission line having reactance XL. It is a double circuit line, and through a transformer with having reactance XT, and of course the reactance of the generator, that is synchronous reactance of the generator, is XS. Okay, so now if the fault occurs at the terminal of the generator, that is at the terminal of the transformer, let us say the fault is a three-phase fault, three-phase to ground fault. Okay, so then in that case your P will become equal to 0 when the fault occurs. Let us say the fault occurs at t equal to 0. So at time t equal to 0, let us say the fault is occurring, so your P will become 0 at that time. At that time your initial angle, that is the stable equilibrium point, is at delta equal to delta naught, right? Already we have seen this. Here in power angle characteristic, you can easily observe this phenomena. That is, from point A, this is your stable equilibrium point, and here at this point the fault occurred, right? And hence your power is becoming 0 here. It will drop down to 0, and then it will accelerate. Your rotor will accelerate in this direction, and let us say delta C, the point where the fault is being cleared. Okay, and in order to find this critical clearing angle, we need to assume that the rotor is moving in the direction up to delta max, which is your unstable equilibrium point, F. Okay, so then we'll find, based on the equal area criterion, if we'll equate these two areas, let us say this is A1, this is A2. If we'll equate these two areas, we'll find the critical clearing angle, right? So if in that case, suppose under such condition, your rotor moved up to this point, and from here again it decelerates. Okay, so then this is the portion, we call this portion as stability margin, because so therefore by definition stability margin can be defined as the distance of the rotor angle from the critical or from the unstable equilibrium point is known as the stability margin. Okay, now this area will give us, if we'll calculate this area, this will give us the stability margin of the system. That means stability margin of the system by which the system, that means by, this is the distance by which the system can be further, if it is disturbed, it can prolongate the disturbance without any without any instability, right? So therefore, this is your stability margin. Okay. So now if we find, if we want, we are interested to find the critical clearing angle. So if we'll integrate Pm minus Pmax sine delta with respect to d delta from delta 0 to delta max, and if we'll equate to 0, we'll have two area here, area 1 and area 2. Both I can, this is your area 2. Area 2. Now if we'll equate both the areas from this equation, then I'll find delta C. Already you have done this in your undergraduate level, so no need to derive, so you can find it. So delta C will be cos inverse Pm by P max delta max minus delta O plus cos of delta max. So this will be your critical clearing angle. And now you're from this critical clearing angle, by just putting this, if you'll substitute this in your swing equation, I will find the critical clearing time Tc. So your critical clearing time Tc will be delta C minus delta O into 2h by pi fs into Pm square root. Okay. Now, if we'll consider one more case where the power will not become zero. When the fault is happening, the power will not become zero. So what is that case? If your fault is not occurring here, it is not occurring here, it is occurring in the midpoint of the transmission line, one of the transmission line. Okay. So in that case, what will happen? Power, electrical power output during the fault will not become equal to 0. That means it will follow another curve, like we can see here. This is your original curve. Okay, that is PE, pre-fault condition. Okay. And now this is your PE during fault. Okay. And now this is your P post-fault condition. Okay. Okay. So what will happen then? When the fault will occur, when the system is operating at stable equilibrium point A, when the fault occurs, as soon as the fault occurs, it will achieve the point B. Okay. And because this point B is less than Pm, that means your PE is less than Pm. Under this condition, your rotor will accelerate and it will move to point C, where the fault is cleared. Okay. So as soon as the fault is cleared at delta C, this point C will move to point E. Okay. what is the meaning of clearing of the fault? Here we can see it. Generally, the transmission lines are the circuit breakers at both the ends, right? As soon as the fault occurs, these two circuit breakers at both the ends will isolate this transmission line. So when the fault will occur here, it will have certain reactance, but as soon as this is removed, this is completely removed, again the XL will be there, right? And therefore the synchronous machine will supply power to the infinite bus. Okay. So therefore your electrical power output during post-fault condition will be greater, somehow greater than the during fault. Okay. So now during fault it will move, again it will accelerate up to point F. In order to find the critical clearing angle, it will move up to, it is assumed that it will move up to delta max dash. Okay, because now with new electrical power output, your unstable equilibrium point will be different. Previously your unstable equilibrium point is at this point, but now with new P, new post-fault electrical power output characteristic, your unstable equilibrium point will move to this point, that is F. Okay. So now now I need to equate these two areas. One is under this and another is under this. Okay. Let us say this is area A1, this is area A2. So if we equate area A1 equal to A2, we'll find the critical clearing angle. Okay. Delta CL. Or you can say delta CR. Okay. Now this shows the area. From delta O to delta C, this will indicate area A1, and from delta C to delta max dash, it will show area A2, right? So therefore, by equating, we'll get cos delta C as this. So is it visible, my screen?
Yes, sir.
Yes,
Yes, sir. Yes, sir. It is visible.
Okay. So now, just by equating these two areas, we'll find delta C, which will be equal to cos inverse Pm delta max dash minus delta O plus P max 3 cos of delta max dash minus delta max 2 cos of delta naught divided by P max 3 minus P max 2. Okay. So this will give us the expression for critical clearing angle. Okay. So this is all about your equal area criterion. So now we'll move to the direct method for assessment of transient stability. So what is the direct method? We talked in the last class. So direct method is your numerical integration of the swing equation. If we can integrate numerically, there are many methods available, numerical methods available. And if we use one of them and we find the response, we can see the behavior of delta and delta omega both. Okay. So we can see So the first method is Euler's method. So Euler's method is a method. This is used for solution of the nonlinear differential equation. That is where fx is a nonlinear function of x. Okay. Now, if the differential equation looks like this, okay, dx by dt equal to fx. So fx is a nonlinear function of x. Then I can write x1 is equal to x plus dx by dt evaluated x equal to xo into delta t. This is very simple. We can see like we are taking delta t as the step, small step, which will be multiplied with dx by dt. That means it will give me delta x. That means I'm finding x1 that is equal to xo plus delta x. So xo is nothing but it is your initial operating point, right? Initial condition. Or you can say if we'll start at steady state equilibrium point or stable equilibrium point, we can move forward, right? With the disturbance condition or without disturbance condition. So similarly, I can write x2 equal to x1 plus delta x, which is evaluated at x equal to x1. So I can write it as x1 plus dx by dt evaluated at x equal to x1 into delta t. So delta t is your step, okay. So this is very important to choose the time step. So as the time step becomes very small, your response will be very accurate, but it will take a lot of time for solution. As the time step will increase very large to a large value, then it will give us a response. Sometime it will not converge also, and it may not give a very accurate result. But it will converge very fast, but it may not give very accurate result, right? So this is known as Euler's method, okay? And just embedded to this, another method was devised that is known as modified Euler method. So in modified Euler's method, it has two steps, okay? So one is your predictor step, other one is your corrector step. So in general, if we'll write this, it will be xk plus 1 will be equal to xk plus dx by dt x equal to xk into delta t. This is in general, right? And here in modified Euler's method, we have two steps. One is your predictor step, other one is corrector step. So these steps in a generalized form are following. So this is your predictor step. Predictor step is exactly equal to the Euler's method. That we can say predictor step as xpk plus 1 that is equal to xk plus dx by dt, which is evaluated at x equal to xk into delta t. And similarly for corrector step, in corrector step, what we do, we'll take both predictor step as well as the corrector step as well as the evaluation at xk and xpk plus 1, and we'll divide it by 2. Okay. Now you can see we'll find a value of x in the predictor step that is used to evaluate dx by dt at x equal to x pk plus 1. And again we are adding the original incremental term, that is dx by dt evaluated at x equal to xk. And when we are taking both the terms, therefore we'll take the average of these two. So therefore we are multiplying half of this. Okay. And of course we'll multiply the step, time step, that is delta t. Okay. So then let us find for the swing equation. This is your swing equation. This is first equation. This is your second equation. Now if we'll apply the modified Euler method to swing equation, these two equations involving the dynamics of the classical model of the power system, that is single machine infinite bus system. Okay. Then for predictor step, I can write this equation. Delta pk plus 1 will be equal to delta k plus d delta by dt, evaluated at delta equal to delta k, delta omega equal to delta omega k, delta t. And the delta omega at predictor step will be delta omega pk plus 1 will be equal to delta omega k plus d delta omega by dt, evaluated at delta equal to delta k and delta omega equal to delta omega k multiplied by delta t. So this is your predictor step. Now if we'll write the equations in the corrector step, of course we'll use both the values that is obtained in the predictor step, which will be used to evaluate this incremental step, and also the previous value of delta will be used to evaluate this incremental step. Both will be added and the average will be taken. Similarly, your delta omega calculated at the corrector step, this one, and your delta calculated at the corrector step is this one. Now these are the new values of delta c and delta omega c, and these are the corrector steps and which is the final values, right? Then it will continue, move forward. Okay. So this is your Euler's method and advanced and your modified Euler method. And there are many other methods also, Runge-Kutta method, then trapezoidal method. There are many other methods we will not discuss further. It may be discussed during your transient stability analysis when it will be taught by Professor Siva Subramanian. Okay. Now we discussed about the classical method of stability analysis. Now, what are the disadvantages of the classical method? So, what are the disadvantages? Already we know there are several disadvantages because this uses the simplistic model of synchronous generator. So therefore the disadvantages are as follows: the rotor flux dynamics, the damper windings and the generator rotor, and the effect of the rotor core and stability are totally behind the synchronous reactance is assumed to be constant on the basis that the rotor field current is held constant, and this assumption is not true, and the rotor field current is controlled through an excitation system and the automatic voltage regulator. Also, it is a well observed phenomena that high gain fast acting exciters can cause small disturbance in stability. Hence, the exciter and the AVR dynamics have to be taken into account. Without this, our study is incomplete. It is assumed throughout the analysis that the mechanical power input is held constant. Again, the input mechanical power depends on turbine speed governor and turbine dynamics, which is very, very important and essential to consider By controlling the mechanical power input according to the variation in the electrical power input, we can improve the transient stability of the system. Hence, the dynamics of the speed governor and turbine have to be considered. So, important generator external controllers like power system stabilizers that improve the system stability significantly, and that need to be modeled and used in the system. So it will be studied, it will be very elaborately discussed in your future classes. Dynamic loads like induction motors, synchronous motors, or electronic devices, etc., can affect the stability drastically. These are not taken into consideration in classical model. Okay. Okay, so your classical model approach for stability analysis is over. Now this is one of the problem. You can do this problem in home and submit this to me as an assignment. Okay, by next week, by next Monday. And also this problem you can consider to apply. I'm writing here this C part, apply your modified Euler method. To find the response. Delta and omega. Delta and delta omega. Okay. So please do this. So this first part and second part, they're very easy. You have to do using pen and paper. A and B part. And C part, you have to do it using MATLAB. Huh? Use MATLAB for this. MATLAB programming you do and submit it to me. Okay. The programs you must submit and along with the assignment sheet. Okay. So this is your figure to this question. Okay. So both are there in the slides. If possible, I will share the slide, or else you can take the snapshot of this. Okay, and do it and submit. Please take the snapshot